The open source thermoacoustic Stirling engine has a very simple design and can use any heat source. It is perfectly suited for generating electricity easily and is designed so that anyone can build it. Almost all parts of the engine can be made with a basic 3D printer. With this video, I want to make the last remaining metal parts accessible to everyone as well. All blueprints and 3D models are being released immediately as open source downloads. I run the thermoacoustic Stirling with self-produced biogas. This allows me to generate cheap electricity from our organic waste. The engine consists of the power core, the feedback loop and the power extraction unit. In the power core, the heat input creates an acoustic oscillation. This is amplified in the feedback loop and then converted into electricity in the power extraction unit. Only the hot section, consisting of the heater, regenerator and thermal buffer tube, cannot be made from plastic. In this video, I want to present a first draft for metal printing and discuss it with you. The final design can then be ordered from a 3D printing service and you just print the rest yourself. I will explain exactly how it works after presenting my design, so you can contribute your hopefully many ideas and improvements. The component made up of the regenerator housing, heater and thermal buffer tube is best designed as a single piece to minimize thermal conduction losses. With 3D printing design, you have complete creative freedom, and there are many ways to optimize the heater channels. To minimize heat losses with my biogas operation, it makes sense to integrate the burner inside the heater. This improves efficiency, but it makes the layout of the heater channels, the secondary air supply and the exhaust gas routing more difficult. Together, the heater channels should have a free flow area of 900 to 1000 square millimeters over a length of 26 millimeters. They need to route into the 60 millimeter diameter of the regenerator housing and the thermal buffer tube without adding too much dead volume or flow resistance. Thin, rectangular slots have a better perimeter to volume ratio than round channels, which is important for maximum heat transfer. I've tested many different geometries and I'm using this design as a draft version for now. You can download the 3D model at ownenergy.org and take a closer look. I'm really looking forward to getting as many creative ideas and improvements from you as possible on how to further optimize the heater geometry. Simple sketches or descriptions are enough. I will then turn them into a 3D CAD model. Once the final design is ready, I already have a contact at JLC PCB who offered to sponsor a stainless steel prototype. Now, let's go over exactly what tasks each individual section has to perform. The regenerator housing holds the regenerator, which usually consists of a fine wire mesh or many small channels. On one side, it connects to the main cooler, and on the other side, it joins the heater. The regenerator is the most important element in the entire engine. Here, an acoustic traveling wave is generated within a Stirling cycle, which is passed on to the rest of the engine as a standing wave. The thermal buffer tube essentially just cools the working gas, so that temperatures in the rest of the engine don't get too high. It connects the heater to the secondary cooler, which cools the working gas down even further. The heater's job is to heat the working gas to the highest possible temperature. At the same time, the flow resistance must not become too high, and it needs maximum internal and external heat transfer surfaces. Now it's your turn. I'm really looking forward to your feedback, suggestions and opinions in the comments, on Discord or at ownenergy.org. If you would like to support the project even further, a membership on Patreon or YouTube helps a lot. Every cent from this goes directly into developing the open source thermoacoustic Stirling engine. Thank you very much for your interest.